What I'll try to do in this session is to give you a very high level overview of what deep neural networks are, what they're capable of, and how they relate to the kind of thing that we have seen in the previous session, which is kernel methods. The goal behind, the goal here in deep neural networks is also to learn nonlinear models. So that is one of the benefits of deep neural networks. They have a lot of other benefits as well, which we'll get into the details of shortly. But again, the theme will be the same. We would like to learn models that are not limited to learning linear patterns. We would like to learn models that can learn, let's say, nonlinear classification boundaries, nonlinear regression surfaces, and so on. Okay, so again, we'll start with the very basic, setup. Linear models have limitations. We talked about it in the previous class, but let's. So again, the idea is that in linear models. So this is kind of a zoomed in version of what a linear model is. We have some data with the D features, and the output is a linear combination of these D features. So Y is sum of WD times X and D. X and D is the Dth feature in the inner data point. So this is what the output looks like. So first case is regression, the second case is classification. If you're doing binary classification, then you look at the sign of this output. Okay, so there are D features with D weights. You compute a weighted combination, and then you either look at the value itself, which in the case of regression, or if you're doing classification, you look at the sign of this quantity. So this summation simply means that you are taking a weighted sum of the inputs that are coming to this node. Okay, so I'm showing you this picture because this picture will be used as a building block in the deep learning, deep neural networks, right? So just keep this picture in mind, and keep in mind what this means. It means that you have these D inputs, each with some weight. You're taking a linear combination of these, okay, which becomes the output. But that's only a linear model. This model is also known as the perceptron model or a neuron model. So this is also known as neuron because it's in some way, this is how we think that brain actually does computation. We have some sensory input, and then it computes some sort of a weighted representation of those inputs to predict then something else is fired in the brain based on that. So without getting into the details of those, the problem with this kind of approach is that this is still linear model, so it can't learn very complex nonlinear boundaries, which is the limitation that we already talked about in the previous class, which led to the basically introduction of kernel methods. Okay, so kernel methods already allowed us to address these limitations of linear models. Right? Now, kernel methods were invented in the early 90s. So that is when people started thinking about how to turn linear models into nonlinear models using kernel tricks. But even before that era, people knew how to solve nonlinear problems. Okay, and that is the era of deep neural networks. So what happened is that deep neural networks were I'm just trying to give you a very high level, very brief historical perspective. So in the late 60s or so, people knew how to design very basic neural networks that can solve nonlinear problems, but computation or optimization of those models was very tricky. But later on, there was a kind of renaissance that happened in this area when people had access to lots and lots of training data to train these neural network models, and also they had lots of computation, like GPUs basically were very popular. So people now know how, people actually have a lot more control over how to train these kind of complex models. So this is area which was earlier known as neural networks is now known as deep learning, and because of the fact that you actually have models with many layers of computations. So typical neural networks can be understood using this idea of what is known as a multi-layer perceptron. So as I said, in this case, this basic model is known as a perceptron. It takes as input a set of inputs, computes a weighted combination. So this basic building block is known as a perceptron, but then you can use it in a sort of hierarchical or a stacked fashion and call it a multi-layer perceptron, where the idea is that in a multi-layer perceptron you will have an input layer where you will have data or inputs coming in. You will have an output layer where you will have the quantity that you are trying to predict, and in the middle you will have a set of intermediate layers which are also known as hidden layers. Okay, because inputs are observed, outputs are also observed, right? At least in the training data. But what you have in between, it's kind of some intermediate representation of data which we don't directly observe, which is why it's known as the hidden layers. Okay? And pictorially you can think of it like this. So this is a very simple multi-layer perceptron with one hidden layer. Okay, so in this case I've taken a very simple example. Yeah. So in this case, just like look at this diagram. So we have a very simple multi-layer perceptron with 3 inputs. So note that we have 3 nodes here. So these are my input nodes. So we can think of this as as an example with 3 features. Okay. And then we have a hidden layer. So we only have one hidden layer. So note that we have a input layer, we have an output layer Y, and then we have one or more hidden layers. In this case, we only have one hidden layer. Okay, and this hidden layer has 2 nodes. So I'm denoting as capital K as 2 nodes. So we have HN1 and HN2. Now, what is this architecture doing? It's taking as input these x's, x1 through x3 for the each. So again, n denotes the training example index, and 1, 2, 3 denotes the number of features, the 3 features. So what this architecture is doing is that it's taking each of these features and it's computing some combination, some linear combination of these features. So note that in each hidden layer you are computing some nonlinear transformation of these features. You are computing HN1 as a linear transformation of these features followed by a non-linearity, which I am denoting by. So note that each of these nodes is, we have a summation first followed by this non-linear symbol, which simply says that whatever is this linear combination, I'll apply a non-linear operation on that. Okay, I'll apply a non-linearity. I'll explain what that non-linearity means. But essentially, you have these inputs and you have these hidden nodes with values being HN1 and HN2. So 2 hidden nodes here in the first layer. So you have HN1 and HN2. Each H and K, where K is 1 and 2 here, can be computed like this. You can think of this as G of this linear combination. So note that this summation is just the linear combination of the inputs, and this G function here denotes the non-linearity that you are applying. Okay? So this non-linearity could be something like a sigmoid function that you apply on whatever is this linear combination. Okay, so as you can see, we have each node in this hidden layer. Each node is also known as a unit, is computing a non-linear transformation of the inputs that it is receiving, right? So note that the first hidden node computes a non-linear transformation of these 3 inputs, where the weights are given by these red edges, the weights of these red edges. Likewise, this HN2 is also computing a non-linear transformation of the same inputs, but using a different set of weights. So the same input has been transformed non-linearly to produce these 2 values, HN1 and HN2, and then on H1 and on these values, you can imagine that you are learning a linear model. Okay, so that's what is going on here. So you have original inputs, you have transformed them into a set of intermediate inputs, and then you are learning a linear model on those inputs. Okay, it's not an it's not a linear model, right? So what you would have is that you in the last, so you have this is the last layer, right? In some sense, last hidden layer. We only have one hidden layer, right? So you take the last hidden layer's value and you apply a linear model on that. Okay, so that's the basic idea in multi-layer perceptron. Now, as you can see, in some sense, we have these 3 features originally, but the hidden layers are also computing a new type of features. Okay, on which you finally apply a linear model. Okay. So in some sense, something similar to what was going on in the kernel methods case is happening here as well. We are taking the inputs, we are transforming it into another set of inputs, and then we are applying a linear model on those inputs. Here the inputs are X, the intermediate, the new representation of the inputs is H, and then the output is Y. Okay. So again, in some sense, we have X being mapped to H, H being mapped to Y. And the overall mapping is nonlinear because of the nonlinearities that you have in the computation of the hidden units. Okay, so overall we will have a nonlinear mapping from the input to output. So let's kind of tease it apart and see what is going on in these steps. So the idea, as I said earlier, was the following: that you take. So again, we will have the same simple architecture with 3 inputs to one hidden layer with 2 inputs, 2 nodes and 1 output node. So these 3 inputs, we first compute a linear combination of these. We'll call them as A and K, which are known as pre-activation in the deep learning or neural network terminology. And then we will apply a non-linearity on, so this is, note that this AN1, the first hidden unit thing, pre-activation is computed as using a linear model. I can write it as W1 transpose X1, XN, right? So this is nothing but simple linear model. Likewise, I can compute another simple linear model for computing A and 2. Okay, so we have the same inputs transformed using 2 linear models, one W1, one W2, giving AN1 and AN2. Okay, then, and these are called pre-activations, as I said. Then you apply a non-linear activation on each of these pre-activations, and that becomes h and k. So h and k is g of a and k, where g is some non-linear function. Okay, I'll give some examples of what this non-linear function is, but this curvy notation simply means that you are applying some non-linearity. It's element-wise non-linearity. So you take every value a and k, just apply a non-linear function so that it's some non-linear version of a and k. Okay, so we have hn1 and hn2, and here are some of the examples of nonlinear activation functions. So you have things like sigmoid, where you take a and then you squash it to a number between 0 and 1. So sigmoid, that's what sigmoid does. So h, the y-axis is the value after applying the activation function, and x-axis is the pre-activation, a and h. So sigmoid will turn a into a number between 0 and 1, h will be a number between 0 and 1. There is something called a tan h activation, which maps this value to a number between -1 and +1. There is something called a rectified linear unit, where this value a, if it is less than 0, it will be set to 0. If it is greater than 0, then it will be set to x. Okay, so this is like a rectified linear unit, and there are some other variants also of this. But the important thing to keep in mind here is that in all these cases, we are getting some pre-activation, and then we are applying this non-linear function g. So g is this curve, you can think, right? Because so note that it's not a linear curve, right? So you have a specific type of non-linearity applied to the pre-activation. Right? So that is and this pre-activation or non-linearity is important in the case of deep neural networks. In fact, almost as important as the kernel function itself was in the kernel methods, right? So kernel functions, allowed us to do nonlinear learning. Here, the main, the key aspect of this architecture is this nonlinearity here. If you don't have this non-linearity, so if you just take a n1, a n2, and just apply a linear, so suppose h1 and hn1 is just equal to a n1, then there's no benefit. You would not be learning any non-linear model. It will just be a linear model. No matter how many times so you can even transform a n1 and a n2 by another linear model, but it will not give you any gain. Overall, the model will still be a linear model. Okay, so it's critical that you apply a suitable non-linearity after every linear transformation, in order to have a non-linear mapping.
So in this case, how do I determine how many that sigmoid function will use at the end?
How many
that function will use? How do you determine that? Using same cross validation?
Sorry, how many sigmoids or how many nodes?
Nodes.
Yeah, right. So so the question is that how do I know if I should use 2 hidden units? So that's
next stage also.
Yeah, next stage, whether I should have more hidden layers, right? Yeah, so those are the architectural decisions that you have to decide based on cross validation, as you said.
There is no other process except this cross validation.
There are. So again, I would probably talk about it if I have time. So one way is to just define a very, very massive neural network and regularize it, okay, which means that you define a very complex neural network with, let's say, tens of thousands of hidden units, many layers, but note that all these layers are connected by connection weights, right? If you regularize these connection weights, and suppose some of the connection weights turn out to be 0, right, it means that you will just drop those things, right? So there are things that you can use to control the complexity. So you can just define a very, very complex model and then regularize it properly, so that only the relevant parts of the network will remain once you are done training. Yeah.
And I want to ask about the choice of the activation function. Like in MATLAB, many functions are available.
Yeah.
So how will I say that which function I will give that will give me a better estimate?
Yeah, see, the answer is the same as how do you choose the right kernel, okay? Again, cross-validation is the typical way of doing it. Okay, maybe you can say first and then.
But they say that there are certain functions that are suitable for a particular type of data.
Yes, so it's true. So these are only some of the activation functions. There are some obvious issues with something like a sigmoid activation function. It was proposed, it was one of the earliest used activation functions, but it has some limitation that it basically, saturates at some point, because, you have the flat thing as you move away from 0, also like in either side. So some of the activation functions have some limitations. So right now the most popular one is ReLU, because it addresses, again, in half an hour I can't really get into the details. That said, there are some activation functions that are very, you can even learn the activation function from data. So in fact, let me just, since I'm talking about the fact. So one thing that you can do is to define an activation function which is general enough and control the hyperparameter of the activation function. So I think I'll just mention, so there's something called, I'm forgetting the name of the function, but I'll just write down the form of the function. So it's something like Okay, so suppose H, I can say that H is A times sigmoid of minus beta times A. Okay, so suppose I define activation function like this, A times sigmoid, so this sigma is sigmoid, and there is a hyperparameter beta. Okay, so there is a beta hyperparameter. If I tune it, so no, you can verify that if beta is very, very large, what will happen? If suppose, okay, so if suppose beta is equal to 0, then what will happen? It will be 1 by 2, so this quantity will be 1 by 2, and H will be simply A by 2, right? So if beta is equal to 0, then it's A by 2. It's just a linear activation function. However, if beta is tending to infinity, then this actually approaches the ReLU function. So you can verify that it will just go to like 0 for beta. For A negative, it will go to beta is actually if beta goes to infinity, then if A is negative, then H will be 0, ReLU, right? Likewise, if A is very, very large, then it will, or any positive number, it will just be like a ReLU linearity. So the point here that I'm making is that you can actually learn the activation functions also. There are many versions, like general type of activation functions. But yeah, as I said in the beginning, it's very important to use the right activation function. So there are some activation functions that are typically like they do fairly well across many data sets, and ReLU is currently the most popular one. But that's not the only one. I mean, there are improvements to ReLU or more general versions of ReLU that you can use. Again, I apologize because it's like I can't really talk about all the details in this like very short lecture. But yeah, keep in mind that whenever you are learning, whenever you are doing deep learning or neural networks, activation functions are probably one of the most important aspects of your architecture. So be careful with the activation function that you are choosing. Okay, so so let's come back to the architecture. So again, you apply the nonlinearity, and then you have H's. These H's now act as features on which you can train a linear model. Okay, so the last layer you compute something like. So note that this is V transpose Hn. This is nothing but a linear model on H. Okay, you compute a score Sn. This is your prediction S. Okay, now this may or may not be your final prediction. Suppose your prediction is a label 0 or 1, or the probability of the label being 0 and 1. Then you can again pass Sn through a sigmoid again, right? If let's say you are doing regression, then Y can just be Sn, Yn can just be Sn. So the final output will be Yn as O of Sn. So again, I'm just keeping the notation a bit generic because this O itself can be identity if Sn is equal, if you have a real valued response, because this S is real valued. So this is R, right? But if let's say Y is the probability of a label being 1, then this O will be a sigmoid function in the last layer. So this is a generic, very general notation. So again, this last layer, the nonlinearity need not be there. If you have a regression problem, then it will just be an identity mapping. But you do need nonlinearities in all the intermediate layers. So by the way, this diagram is the same as the previous diagram. I'm just like dissecting these nodes to clarify what is going on here. So you have linear maps followed by nonlinearity, then a linear model, and then another optional nonlinearity can be there in the last layer. Okay. So this is the like very bare bones architecture of a very, very simple neural network with just 3 inputs, one single layer with two hidden units and one output node. Okay. Yeah. So again, this is the picture that I had before. So the same architecture that I showed, you can compress these two things into one, which is why. So this is the summation followed by nonlinearity, which is why I split this node into 2 halves. Like bottom half is computing the linear combination, the upper half is doing the nonlinearity. So this is the typical notation that you would see in other books as well. Okay. Okay, so again, H and K is in this case we have one hidden unit. There can be more than one hidden units as well. So H and K denote the value computed by the kth hidden unit. Okay, so H and K is the value specific to the nth input. So you have nth input, H and K is the value of the transformed version of the nth input computed by the kth hidden unit in a single layer neural network. Okay. Also, in some neural network architectures, if you have many hidden layers, you can even have different activations. Even the activation function can be different across different layers. Okay, so the basic idea here is that we are taking these features, we are applying some nonlinear transformation to get a new set of features, and then we are learning a linear model, right? So that's how we are able to do nonlinear learning. Okay. Now let's look at let's look at another simple illustration of why this is actually learning a nonlinear model. It kind of intuitively makes sense that we are applying a nonlinear mapping. So sure, we are transforming data into some nonlinear space, and then we are actually learning a linear model, effectively nonlinear. But let me just like give you a very simple illustration, hopefully simple illustration that will clarify the idea a bit more. So one way to think about this multi-layer perceptron, this very multi-layer perceptron, is that it's kind of a composition of multiple models. Okay, we are learning a single model, X to Y model, right? But in some sense, even this very simple model can be thought of as a combination of two models. One model is taking X and computing H and then using that to compute Y. The other model is taking X, computing H, and using that to predict Y. So we have these two models like being combined together to produce Y. One model defined by the weights. This branch is one model, the second branch is the second model, right? It's a superposition of two models. This is a very simple example, but if you have many hidden nodes, you will have superposition of that many simple models. So deep learning models are basically superpositions of many simpler models, each being a linear model followed by nonlinearity, right? Right. So this is example will hopefully clarify that. Suppose you have a classification problem. So let's look at a very simple example. So this is our classification problem. Blue and red points. I need to learn a classifier that separates the points. Do you think a linear classifier will do a good job here? Probably not, right? Because we have all the points, red points coming lying in between. So a standard classifier which just does this. So note that in this case we have two features, x-axis and y-axis. So these are the two features. So I can try to learn a model like this on the left hand side. It will not do well because it's a linear model. However, I can also apply a model like this, which again, this is even a simpler model. We only have two features here at the bottom layer because the data only has two dimensions, right? So this is another model that I can apply. So this is a multi-layer perceptron with two inputs because we have two features for every data point. We are computing these two intermediate inputs, Hn1 and H12, and then we are taking a linear combination. Okay. So why is this model able to learn? Why would this model be able to learn a decision boundary for this data? Okay. So let me just show you the reason why that happens. Okay. So this picture is what you should keep in mind. This is just a zoomed in or expanded version of the same picture. So we have inputs. So suppose we have a simple sigmoid nonlinearity. So we are not even using ReLU, right? So I take these two inputs. If I take a linear combination and then if I apply a sigmoid, I learn something like this. So x1 and x2 are two features, and the sigmoid looks something like this, right? So it will be like so the height of the sigmoid is the score of this input, right? So the larger the score means the probability of being 1. The closer the score is to 1, the larger the probability is. So suppose this branch is computing this kind of a sigmoid function. The second branch can also be used to compute another sigmoid function, right, with some other parameter because the weights are different. So both these so note that these are just logistic regression models, right? So you have seen logistic regression, right? So these are just two simple logistic regression models. Now once I have these two logistic regression models, I can just combine them. In some sense, I can add them. Okay. Now if I add them in a certain way, I can actually learn a nonlinear decision boundary. So for example, if I take the first one, if I multiply it by 1, and if I take the second one, and if I multiply it by -1, then it will just flip the direction, right, of the second thing. So it will be like small here, large here, right? So because I'm multiplying by a weight -1. So if I take the first logistic regression model, applied and multiplied by this artificial weight 1, let's say, second one and multiplied by -1, then I'm kind of taking this sigmoid that is small here, high here, and then the second one that's small here and high here. If I add them, effectively I will get a curve like this, right? So the overall score of any input, because I'm trying to predict a probability, will be small in some regions. Like in this region it's small, it's in that region it's small, but it's kind of large in the middle, right? And in a two-dimensional space, this is the kind of function that I would like to learn for the data that I have, because you can see that suppose the red ones are the positive points, right, and the blue ones are the negative points. So I want large score for the points in the middle region and small score for the points that are in the regions away from that, and that's essentially the behavior that is being captured by this simple composition, right? So that's the idea that we have taken. So it's kind of a composition of two functions, two sigmoids added suitably, right? But note that it's not that I'm fixing these weights. These weights will be learned by, by the optimization procedure. So that's the underlying idea, that you have just a simple composition of two functions that is giving rise to a nonlinear function. Okay. Now, so this illustration is only for two functions, but in general, you can have the number of, so depending on how many units you have, you will have a composition of that many functions. Yeah, so this is the idea. You can of course generalize it to more general cases. So here I have k hidden units, the same idea, the same illustration that I had earlier. Now I'm assuming that we have d features, one hidden layer with k features, and then the last layer is just a linear combination of these features. So the same idea generalized to now general d, k, and but again it's a single hidden layer. So I'm still using a single hidden layer in the notation. These weights, note that this big W denotes the set of all weights that connect the nodes between these two layers. So you can call this W as W1. So this W can be thought of as a matrix whose size will be d by k. Okay, because you have dk pairs of nodes, right? So W can be thought of as a W1, W2 up to W capital K, where Wk is, you can think of Wk as the vector that connects to the kth hidden unit. So Wk, so all these reds are the weights that connect to the first hidden node. I can call all these red weights as W1 vector. What is the size of W1 vector? D. Likewise, W2 will be the set of weights that connect to the second hidden unit. W capital K will be the set of nodes that connect to the kth hidden unit, and so on. And collectively, I'm calling them as big W. Okay. Now, in some sense, you can kind of see what these weights are doing. Each of these weight vectors, so each W1, W2 up to W capital K are weight vectors, right? They're kind of transforming the inputs to learn some feature vector, right? So H and K. So W1 will learn the first feature. It will kind of detect how, so suppose, so W1 is kind of a feature that is present in the data. If you take the inner product of W1 with this X vector, it will kind of see how much the first feature is present in this input, and that value will be given in this, will be the value of H1, N1, right? Same thing will happen with every hidden unit. And then once you have extra, so in some sense these W1 through W capital K are feature extractors or feature detectors, right? So you have, so these are doing all the hard work for you for extracting the features. Once you have the good features, you simply apply a nonlinear model. Sorry, linear model on top of it. Before that you apply a nonlinearity here. So this simple case, by the way, assumes only a single output, Y, but in many cases you have multiple outputs to be predicted. One simple example is that suppose you have a multi-class classification problem. So typically in binary classification, we just want to predict whether Y is 0 or 1. Okay. In regression, we want to predict whether Y is some real valued number. On the other hand, if we have, let's say, a multi-class classification problem where we are trying to predict which of the, let's say, L many categories. So suppose I'm trying to predict, which of the 100 type of animals this image is of, right? So then Y will be a vector of that many dimensions. So that can also be used here. So suppose I have C many classes, so I can have one output, node for each class. Okay. And I can have the same, so this is just a simple extension of what I had. So rather than learning a one single linear model for one output, I'll have as many linear models as I have the number of outputs. So this is yn1, yn2 up toync. Yeah, so this is the most general way of representing the neural network, because in many cases you do have multiple classes if you're doing multi-class classification. The same architecture can be also generalized. So far I was assuming that there's a single hidden unit, but there's no restriction, you can actually have multiple hidden units. Multiple hidden layers. And that is when it becomes even more interesting. Now the idea is that if you have understood the single hidden layer case, then it's kind of straightforward. What happens is that the outputs of the first hidden unit, they just become input for the next hidden unit. Next hidden layer, outputs of the first hidden layer become input for the next hidden layer. And this keeps on continuing. So you have now I'm using different set of weights for connections between every pair of layers. W1 is the weights of this layer, W2 is this layer, and so on. So you now have a series of layers. You have, let's say, capital L many layers, hidden layers, and the number of hidden nodes in each of these layers is K1, K2 up to K capital L. Again, these numbers have to be decided based on some cross-validation criteria, or as I mentioned in the beginning, you can keep these numbers very, very large and have a strong regularization, which will learn the appropriate relevant number of hidden units and also the hidden layers. So again, this is a kind of a model architecture question. There's a lot of research on how to appropriately figure out what is the right architecture. Right now, so one of the limitation of, so I'll just kind of mention briefly in passing that this is a very complicated network, because if you have, let's say, 100 layers and maybe in every layer you have maybe 100 or 200 nodes, there are going to be lots of parameters that you have to learn, right? Because you have so many weights that you need to learn in such a model. Now, suppose you want to store and deploy this model on a smartphone device. You clearly, smartphones don't have that much memory, right? Or maybe this is the era of Internet of Things, IoT devices, very tiny devices with let's say very few kilobytes of memory. You clearly can't store these kind of models in those memories, right? Because these require megabytes of maybe or gigabyte of memory to just store the models. So there is also a lot of work on compressing these models so that you don't sacrifice much on the prediction accuracy, but you can still have maybe a much smaller number of parameters in the model. Again, this is something that is beyond the scope, but I just wanted to mention that one of the limitations or shortcomings of these kind of architectures is that they require a lot of parameters to be learned, and it can be very expensive to store them in memory. Okay. So there is a lot of work on this so-called area of deep model compression. So if you are interested, so you can. So again, I mean, the name itself is very generic, deep model compression, which simply means that taking, so you can train a model, deep learning model, but you can then try to prune it in some way so that you don't lose much of the predictive power of the model. So there's a lot of work on that. So by the way, so this architecture, I think I did not mention the name earlier also, earlier that this is also known as a fully connected feed-forward network because of the design of the architecture, because there are no like backward connections and only the units between adjacent layers are connected, which is why this architecture is also known as feed-forward neural network. The earlier name that I talked about was MLP, multi-layer perceptron, but MLP is equivalent, it's the same, they are synonymous basically. So yeah, so here's the interesting thing that you should, that's kind of a takeaway from this lecture and the previous lecture. Even this lecture, as I mentioned earlier, this is kind of doing feature learning. It's taking some inputs, it's transforming these inputs to some final good set of features and then applying a linear model. So you can just like abstract away whatever is there in the intermediate layers and simply call it phi of xn, right? So xn coming in, there is some like complicated deep neural network that is doing the transformation for you, phi of x, and then final prediction is made on phi of x. V transpose phi of x. Okay, so this phi of x is kind of similar to how we did in the case of kernel methods, right? But in the kernel methods, phi of x was defined based on the kernel you were using. Here, phi of x is being learned from data. Okay, by defining a deep neural network with a appropriate architecture with some nonlinearity defined, right? So it's but it's being learned rather than decided by the, because phi of x will depend on all the parameters w1, w2, w. So whatever is these values, they will define what the final h will be. So which is why we typically say that a deep neural network is a feature learner. Right? So this phi is a feature representation, it's a learned mapping. So that's one of the key differentiators from a kernel method, because their phi of x is defined the moment you define the kernel function. So if you define k of xn comma xm, it automatically defines what phi of x will be. Whereas here, phi of x will depend on what the neural network is. That said, and again, we can't really get into the details of, there are connections between the learning, the features that are learned by neural network and what is learned by kernel. So at some level they are related. So people have studied these connections in a lot of detail, but it's just different way of thinking about it. That here you have these transformations that are giving you these features, and in the kernel case you actually have just a kernel function, right? But the point is that even the kernel functions can be learned. There's a lot of literature on learning kernel functions, and neural networks are just by definition they're based on learning the transformation. Yeah, so again, this is, you can think of everything that happens between the input layer and output layer as a black box that gives you phi of x. Okay, so that is what is done by a neural network. A couple of other points that, as I said in the beginning, a neural network can also be thought of as a feature detector. So that is one of the nice properties of a neural network, and it is especially useful for cases when you are working with image data, images or natural signals, that you can think of these hidden units as detecting specific types of features in the data. Now, as I mentioned, all the weights that connect to a single hidden unit here, they can all be thought of as detecting a specific type of feature. Okay. Now, suppose you have 100 hidden units in the first layer, you would have 100 weight vectors, each of the weight vectors connected to one of the hidden units. So in this case, I have shown you these tiny pictures. So we have 100 images, and each of these images can be thought of as edges that may be present in images. So different types of edges that may be present in a given image. So in some sense, these 100 units are detecting whether certain types of images are how much or whether a certain type of edge is present in the image, right? So in some sense, this layer is learning an edge-based representation of the image. As you go higher up in the layer, so again in this case, I'm assuming that the data was face images. So suppose I'm doing face recognition or face classification task. So as you go to the higher level layers, the feature again higher. So in the first layer, you are detecting features in the original input. In the higher layers, you would detect the features present in the features from the layer below, right? So suppose if this layer is learning edge-based features, then the upper layer will learn features of features, like composition of edges, which are in this case maybe parts of a face. Okay. As you go even further up layer, so again in this case I am deliberately showing you a smaller number of layers in the above layer, like 32. So in this case, let's say there are 32 types of face parts, and then each unit will tell you how much of that face part is present in the given image. Okay. And as you go further and further up, you can see more and more holistic features being detected by this network, which is why we typically think of neural networks or deep neural networks as feature learners, where they learn features at multiple levels of granularity. So the bottommost layer will detect very primitive kind of features, and the higher level hidden layers, they will detect more and more complete or more compositional style of features. Okay. So that's about it. I think I'm already running out of time, but so this image is this is also kind of showing you why neural networks are beneficial. So I'll give you this very simple example that this will illustrate why having multiple hidden units and maybe one or more hidden layers helps. Suppose my task is to predict whether an image is 4 or not. Okay, so suppose this is a binary classification task. I have, let's say, now the digit 4 can be written in a variety of ways. Now suppose I learn a linear model for classification, where given an image, it will predict whether the image is 4 or not. A linear model will try to learn a single mapping. So this is like the image pixels, and then you'll have a weight vector W transpose X. If it is, let's say, greater than 0, it is 1. If 4. If it is less than 0, it is like 0. If it is not 4, then this single layer model will kind of learn what an average 4 looks like. Okay, because it only would try to learn a single pattern. Okay, this is what it's a single layer, simple, model. So it will only learn to detect what a generic 4 looks like. Okay. But we know that the digit 4 can be written in a myriad number of ways, right? So lots of ways we can write it. So a single layer model with a single output node is not good enough. However, suppose we go to this neural network model where we define, let's say, k hidden units. Now this has a lot more flexibility, because each hidden unit can try to learn a specific a specific way of writing the digit 4, right? So suppose there are k many ways of writing 4, maybe k could be any number. So each unit will kind of like learn to whether it was 4 was written in this way, or maybe 4 was written in this way, at least one of these would be true, right? Whereas this capability is not here, because this is saying that, well, if the digit doesn't conform to this average 4, then it's probably not a 4, right? So it's kind of more, you know, generic in the sense that what 4 looks like, whereas here you can actually define, you know, or learn what are the various ways people write 4, the digit 4, and based on that it can kind of take a vote or composition of all these predictions, right? So I'm just trying to give you a high level intuition as to why this kind of why neural networks help, because they can help us learn the nuances in the data, like what kind of different ways the same data, same object, like in this case the digit 4 can be represented, and then the different hidden units can try to detect and work together to make the final prediction. Okay. Now again, I think I don't have time to go over this. Now the basic idea that, you know, we have is that we have this deep neural network with all these weights, right? So between the input layer and the hidden layer, and also in the output layer, these weights have to be learned, right? So you, at the end of the day, you have to solve some optimization problem. Okay, so you must have seen the loss function, right? So you have output minus, you know, some transformation of the input, where the transformation is defined by the weights, and then you have to minimize the loss function by solving some optimization problem using maybe a gradient method and so on, right? So you have to apply an optimization problem in the end. The specific type of optimization procedure that is used to train deep neural networks is known as the backpropagation algorithm. Again, we don't really have time to go over it, but the idea is that you don't have a single layer here, right? That you can't just take a gradient once and set it to 0, or maybe do gradient descent. We have a chain of, you know, operations here, possibly multiple layers. In this case, just 2 layers, but you can have more than 2 layers. So how do you do these computations, gradient computations, in an efficient way is what backpropagation is about. So again, I don't really have time to go over it. Let me see if I have anything else. So again, it's basically chain rule, using chain rule to compute gradients. It's basically gradient descent, but done in a clever way so that you can reuse some of the computations when you're doing gradient descent. So I won't really have time to talk about activation functions. I already talked about in some detail, so I'll skip this part as well. So I don't think so the one thing that I wanted to emphasize upon is that which I already mentioned is that a deep neural network or a neural network with even one hidden layer can be seen as a composition of multiple functions. The more functions that you add, right? So because as you can imagine that if I increase the number of hidden units, the complexity of the function that I am learning is going to increase, right? As you can see here, suppose I have k equal to 3, then suppose I have these red versus green points, and I'm trying to learn a classifier for them. If I use, let's say, 3 hidden units, then my function might look like this. If I use, let's say, 6 units, then my decision boundary might look like this. If I add 20 units, because you can see that in the simple case that I showed 2 sigmoids, right? You learn this like bumpy kind of a score function. But if I add more sigmoids from different directions, I'll learn a very complicated decision boundary. That is what will happen here also. The more hidden units you are adding, the more complex the function that you are learning is becoming. Okay, so let's say with k equal to 20, it will be very, very complicated function, right? You may not want that complicated because you might be now overfitting, right? So you have to somehow keep a way to control the overfitting, and there are many ways to do regularization in these models. So you can actually keep k as very, very large, but you have a very strong regularization. There's something called dropout. I don't know, those of you, so there is a very popular procedure called dropout, which is very, very effective to control the complexity of a deep neural network. The idea is that you at the time of training, you randomly drop one of these things. You set all the weights incoming and outgoing from this unit to 0. So that's again, we can't really get into the details of dropout, but if you're interested to see how you can use regularization in deep neural networks, dropout is one of the most effective strategies that is available out there. Yeah, so I think I kind of am done with it. One thing that I wanted to mention before we conclude is that so there is a very fundamental theorem that I think I did not yet talk about, is the theorem called universal approximation theorem. So you should keep it. So it basically says that theorem. So what the universal approximation theorem, this is by Hornick. So what this theorem says that if you have a deep neural network with one hidden layer, which is sufficiently wide, if you have lots and lots of units in this like a hidden layer, suppose you just have one hidden layer, that neural network can approximate any function. any function. So that's a like very strong statement. Right? So if you have a deep neural network, the very first one that I showed, but if you have potentially infinite many hidden units, or maybe very, very large number of hidden units, it can approximate, it can learn any function. Okay. So and that is what, so that's a theoretical result, which is why people got excited about deep learning, that well, I can just construct a deep neural network with very wide hidden units, and then I'll be able to learn any function. So why not just use the neural network with one hidden unit with lots and lots of functions? Why bother about having this hierarchical architecture where we have multiple hidden layers? Now both extremes are fine. I mean, both will in principle learn the function, right? But there are some benefits, so which is why I have titled this slide as wide versus deep. So should you go for one hidden unit with lots and lots of one hidden layer with lots of units, or many hidden layers with moderate number of hidden units? Well, typically you prefer this kind of architecture because it also allows you to learn these nice features in the data, because because you can actually learn different types of features that are capturing different types of properties in the data. The other benefit is that if you have this kind of these kind of multiple layers, you are also reducing the data dimensionality. You can reduce the data dimensionality because you can say that, well, this K3, the last hidden layer, can be some small number, okay, which will effectively give you a way to reduce the data dimensionality, because D can be very, very large, but let's say in this case K is 24. So in that sense, if 24 is smaller than D, then I'm also reducing the data dimensionality. So I'm learning a deep neural network, I'm learning this powerful function, but at the same time I'm also reducing the data dimensionality, which will not be the case if I learn a very wide single layer hidden neural network, because K would typically be very, very large. So even though I'm able to learn the function, nonlinear function, I'm not learning a good representation of data or a compressed representation of data. So in that sense, a deep neural network is also useful for just doing data dimensionality reduction. Okay, so this is, by the way, a supervised learning setup, but you can also use deep neural networks to do unsupervised dimensionality reduction, which is known as autoencoders. So the idea in autoencoder is that you can have, let's say, some input X, then you have a neural network which will compress it into, let's say, some H, and then you will have another neural network which will uncompress it. So the output, if you make the output equal to the input, then you're trying to take input and then transform it and then uncompress it to get the same input. So which is why it's known as autoencoder. So that's the, now this is an unsupervised model. If you just want to compress data, then you can use something like a deep autoencoder, where the mapping between X to, so it's something like PCA where you compress the data, right? But in PCA you only do it using a linear model, right? But with the neural network you can actually have the X to H mapping as a nonlinear mapping, and then H to X mapping also as a nonlinear mapping, because they are now being learned by a neural network. Okay, so I think I'll not be between you and the lunch, so I think I'll stop here. Are there any questions, or I know this was deliberately meant to be short. I really can't cover all the details that I would have liked to cover.
So
Differences between this and kernel methods?
So differences.
Sorry, I thought differences, yeah. So differences, so I think I'll give the slides. I don't have any references as such in the slides itself, but I can add a couple of, you can also access some of the, well, no, I think not from my webpage. What I'll do, I'll add an additional slide with some readings from appropriate sources where you can learn more about these things. I'll also have references for the kernel lecture that I gave. So I'll add those references and then send it to Raghu, and he will share it with you. Okay? Yeah, so yeah, I'll stop here then. Yeah, thank you.
Thank you, sir.